Welcome to the ultimate mind-bending exploration of what it truly means for something to be real. For centuries, philosophers and science fiction enthusiasts alike have been grappling with this age-old question. But now, thanks to the groundbreaking work of Nobel Prize-winning physicists, we have a brand new perspective on this long-standing debate. According to the principles of local realism, objects in the universe possess distinct, inherent properties that exist independently of human observation or measurement. But what happens when we delve into the mysterious and complex world of quantum mechanics? Enter the legendary physicists John Clauser, Anton Zeilinger, and Alain Aspect, whose groundbreaking experiments have challenged the very foundations of local realism. For decades, these pioneering scientists have conducted mind-boggling experiments that have left us questioning our understanding of the universe. Their work has shown that the principles of local realism are likely to be false under the rules of quantum mechanics. The universe may not be as real as we once thought. So buckle up and prepare to have your mind blown as we take a deep dive into the world of quantum mechanics and explore the implications of these groundbreaking findings. The work of Clauser, Zeilinger, and Aspect represents a major paradigm shift in our understanding of the universe and challenges us to question what we think we know about the nature of reality. Get ready for an exhilarating journey that will challenge your beliefs and leave you questioning everything you thought you knew. Quantum physics. The world of quantum physics is a strange and mysterious place, where even the greatest minds can find themselves lost in a sea of uncertainty. But recent discoveries have shed new light on this enigmatic realm, and the Nobel Prize-winning work of John Clauser, Alain Aspect, and Anton Zeilinger has turned the scientific world upside down. At the heart of quantum physics is the idea that the universe is random and unpredictable, and that particles exist in a state of quantum superposition until they are observed. This means that a particle can exist in multiple states simultaneously, and it is only when it is observed that it collapses into a single definite state. But why does this happen? This is the so-called measurement problem, and it is one of the greatest mysteries in all of science. Despite decades of research, scientists still do not fully understand the nature of the wave function or the process by which it collapses. However, the work of Clauser, Aspect, and Zeilinger has provided new insights into this problem and has challenged long-held assumptions about the nature of reality itself. Their groundbreaking experiments with entangled photons have established the violation of Bell inequalities, which overturns the principle of local realism and suggests that objects do not exist independently of observation. This work has opened up new possibilities for the development of quantum sensors and quantum computing, and has transformed quantum information science from a fringe area of study to a vibrant and important subfield of physics. Without the pioneering work of these three physicists, our understanding of quantum mechanics and entanglement would be incomplete. In the strange and unpredictable world of quantum physics, nothing is as it seems, and reality itself is called into question. But thanks to the groundbreaking work of Clauser, Aspect, and Zeilinger, we are closer than ever to understanding the mysteries of this strange and fascinating realm. If you have followed us this far, we love you, and so take a moment to like this video and hit that subscribe button. So let's move on to the next wonderful item we have in store for you, exploring the implications of Bell's theorem. Let's step into the captivating realm of quantum mechanics, a theory that explains the behavior of the microscopic world. Developed in the early 1900s, this theory makes precise predictions about experimental results but also challenges our perception of reality. Among the many enigmas in quantum mechanics, the problem of non-local realism stands out, which raises the question of how particles can communicate with each other instantaneously across any distance. The problem of non-local realism was first introduced by three physicists: Albert Einstein, Boris Podolsky, and Nathan Rosen, APR. In their 1935 paper, the trio proposed a thought experiment involving pairs of particles sent to two observers, Alice and Bob, stationed at opposite ends of the solar system. According to quantum mechanics, particles lack properties like spin until measured. Alice measures her particle and finds it to be either up or down, and Bob's corresponding particle must be the opposite. The conundrum is how particles know what Bob's will do as they fly out of the solar system in the other direction. This led to EPR's key question: if Alice's particles lack a spin until measurement, how do they predict Bob's particle's behavior? To explain this puzzle, physicists proposed hidden variables, factors that exist in some imperceptible level of reality. These hidden variables would allow nature to recover local realism denied by quantum mechanics. However, this did not catch on among physicists, who accepted quantum mechanics as is. Physicists did not want to think too hard and preferred to shut up and calculate. This lack of interest persisted in part because highly regarded scientist John von Neumann had published a mathematical proof in 1932 that ruled out hidden variable theories. Although von Neumann's proof was later refuted by mathematician Gray Herman, physicists did not take notice at the time. In modern times, experiments have reinforced quantum mechanics' most mind-boggling tenets, showing that nature is not locally real. Particles lack properties until measured, and they seem to communicate with one another no matter the distance. Although the outcomes of measurements are random, these correlations cannot be used for faster-than-light communication. Despite the difficulty in understanding quantum mechanics, it accurately describes the microscopic world and has led to new technological advances. The problem of non-local realism persisted for 3 decades before being shattered by physicist John Bell's 1964 theorem. Bell was bothered by quantum orthodoxy and sympathetic to hidden variable theories. He was inspired by physicist David Bohm's non-local hidden variable interpretation of quantum mechanics. Bell recognized the same flaws in von Neumann's argument as a side project to his job working as a particle physicist at CERN and developed a theorem that dragged the question of local hidden variables from its metaphysical realm onto the concrete ground of experiment. Bell's theorem showed that under precise circumstances, an empirical discrepancy between local hidden variable theories and quantum mechanics could emerge. The eponymous Bell test, an evolution of the EPR thought experiment, involved Alice and Bob receiving the same paired particles with different detector settings, which threw off apparent telepathy. Quantum mechanics predicted entanglement or perfect correlation between particles when both uppercase or lowercase settings were used, while local hidden variable theories could not account for this. Bell's theorem languished unnoticed in a relatively obscure journal for years, despite its potential to help determine the nature of reality. Hashtag the Bell test and the challenge to quantum mechanics. In the late 1960s, a young graduate student at Columbia University named John Clauser stumbled upon a paper that would change the course of his life. The paper was written by a physicist named John Bell and explored the possibility of hidden variable theories in quantum mechanics. Clauser became obsessed with the possibility of proving these theories correct, and with Bell's encouragement, he set out to conduct the very first Bell test. With a kayak-sized contraption, Clauser and his graduate student Stuart Friedman fired pairs of photons toward detectors that could measure their polarization. Although their analysis yielded strong evidence against hidden variables, the result was not conclusive due to various loopholes in the experiment, including the locality loophole. But Clauser was not deterred. In the following years, a young French optics expert named Alain Aspect proposed a way to close the locality loophole by changing detector settings while photons were still in flight. Aspect's experimental results only strengthened Clauser's findings, making it highly unlikely that local hidden variables existed. Bell himself was amazed by the implications of these tests, stating, "Perhaps nature is not so queer as quantum mechanics." But the experimental situation is not very encouraging from this point of view. Despite the potential to determine the true nature of reality, Bell's theorem was initially overlooked in a relatively obscure journal. It wasn't until 1997 that Anton Zeilinger and his team conducted a Bell test over a distance of nearly half a kilometer, improving on previous experiments. But closing the remaining loopholes proved to be a challenge, requiring a giant systems engineering project. Zeilinger's team eventually found a perfectly straight, unoccupied 60-meter tunnel in the dungeon of Vienna's Hofburg Palace, allowing them to conduct an experiment that closed multiple loopholes at once. Their results, published in 2015, coincided with similar tests from 2 other groups, all of which found quantum mechanics to be flawless. The creation of an experiment closing multiple loopholes was a true feat of scientific ingenuity and a testament to the tireless work of generations of researchers who refused to settle for superficial explanations of the universe. The Bell tests and their significance in the field of physics. In the mid-20th century, the field of physics was shaken to its core when a brilliant mind named John Bell revealed that the foundations of quantum mechanics went against the traditional concept of local realism. This notion stated that the results of experiments were determined solely by what occurred in their immediate vicinity. Bell's work set off a chain of events that would challenge the very fabric of our understanding of the universe. In the following decades, scientists conducted a series of groundbreaking experiments called Bell tests, designed to put Bell's theory to the test. The first tests were conducted by the brilliant physicist Alain Aspect in the 1980s. Although these early tests had loopholes, they paved the way for more sophisticated experiments to come. Enter Anton Zeilinger and his team, who worked tirelessly to close the loopholes in the Bell tests. For several decades, they succeeded in their mission. Their hard work and dedication finally put an end to one last loophole in 2016, with the successful completion of the cosmic Bell test. These tests confirmed beyond a doubt the accuracy of quantum mechanics and the impossibility of local hidden variables. The significance of these tests cannot be overstated. They allowed physicists to delve deep into the mysteries of the universe, without the limitations of human intuition and aesthetics. With the questions that had once been considered taboo, they were able to push the boundaries of knowledge and understanding. It is for this reason that the 2022 Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger. However, it is also a testament to the tireless work of all the researchers who have ever questioned the superficial explanations of quantum mechanics and who have sought to uncover the true nature of reality. The Bell tests have opened the door to a whole new world of discovery, and the future of physics is brighter than ever. Despite the difficulty in understanding quantum mechanics, it accurately describes the microscopic world and has led to new technological advances. We hope you have enjoyed this mind-bending exploration of what it truly means for something to be real. Please like this video and hit that subscribe button for more fascinating content.